Okay, now let me introduce my report. Good day, ladies and gentlemen. Now let me introduce our recent work about the project application and popularization of vanadium microalloying technology in X80 pipeline steel in China. The presentation will cover the following 6 aspects. First, the introduce background of the project briefly. Second, objective and the schedule of this project and achievement up to now. Third, my report content of the previous meeting. Fourth, research progress from last meeting to now. Fifth, communication with other institutions about X80 pipeline steel with vanadium. And the last one, the next work plan. Now this is the research background. List of oil and gas pipeline in China is increasingly rapid. Till the end of 2020, the length of oil and gas pipeline has arrived 144,000 kilometers. It is reported that in 2025, the length of oil and gas pipeline will be 240,000 kilometers, which means the demand of pipeline steel will be more than 3 million tons per year, and especially demand for X80 pipeline steel will be no less than 1.5 million tons per year in recent years, which is a huge number. China began to promote the use of X80 pipeline steel on a large scale in the second West-East National Gas Transmission Project in the year 2009, with the application of niobium microalloying technology. Low carbon and high niobium has become a typical composition system of domestic X80 pipeline steel. However, high-grade pipeline steel made in China doesn't contain vanadium. As an effective green refining element, niobium plays an important role in the strengthening of pipeline steel. In China, most steel mills produce X80 steel by adding 0.065% to 0.085% niobium. However, in recent years, weld failure accidents have occurred in the high-grade pipeline projects, especially in the girth weld. Niobium promotes the formation of granular bayonet, and a large number of porous martensite and austenite components appear in the structure, which weaken the toughness of the weld. With the increase of niobium content in the base metal, the low temperature toughness of the weld decreases. Recent research results of our team show that reducing niobium content and increasing vanadium content is conductive to improve the toughness of the hot effect zone of the girth weld. So we can make an assumption that niobium content in the pipe would be reduced, and niobium plus vanadium composite microalloying would be used to guarantee the high strength, meanwhile increase the toughness of weld. As demand for X80 pipeline steel will be no less than 1.5 million tons per year in recent years, if 0.02% to 0.04% vanadium was added in X80 pipeline steel, demand for vanadium would be a huge number. The aim of this project is to promote the application of vanadium in X80 pipeline steel in China. According to the plan, we have got 3 kinds of X80 pipeline steels. Number 1 contains 0.08 niobium. Number 2 contains 0.05% niobium and 0.03% vanadium. And number 3 contains 0.03% niobium and 0.05% vanadium. Through thermal simulation experiment and microstructure observation, the exciting state of niobium and vanadium in slab heating stage is studied, and the morphology characteristics of austenite grain during reheating and rolling stages are described. The effect of niobium and vanadium on austenite grain characteristics is obtained. Through the study of phase transition, a phase transformation law of 3 steels are obtained. And today's step, laboratory-based basic research on vanadium microalloying steels is completed. The next step is industrial trial production of vanadium microalloying X80 pipeline steel. Here are the research results of previous meeting. 3 kinds of steels with different niobium and vanadium content are obtained in lab. Chemical content of number 1 steel is the same as X80 pipeline steels manufactured in steel mill in China, with a conventional idea of low carbon and high niobium. But when it refers to number 2 and number 3 steel, based on the metallurgical composition of number 1 steel, content of niobium is decreased and the vanadium is increased, which is so-called niobium and vanadium composite. 3 steels are obtained according to the same production process by controlled rolling and cooling, just like the industrial production process, TMCP. As the mechanical properties shown in the table, strength and toughness of 3 steels fulfill the technical requirement for X80 pipeline steel. And here are also the achievements of previous stages. At the slab reheating temperature of 1180 centigrade, vanadium is completely dissolved in all experimental steels, but niobium is only partially dissolved in number 1 steel with a content of 0.068%. Niobium in number 2 and number 3 steel is completely dissolved. In the reheating stage, with the extension of holding time and the increase of temperature, the grain size of austenite is coarsening, and the austenite of number 1 and number 2 steel is kept in a relatively fine state. After the reheating process, the precipitated phase is many large-sized particles, and the dragging effect of solid solution atoms plays a major role in hindering the growth of austenite. For the reheating stage, 1180 centigrade and 90 minutes is the target process parameter, in which condition the niobium and vanadium elements are basically solid solution and the austenite grains are finer. And now I will introduce some results of our recent work. Through thermal simulation experiment, microstructure of austenite is observed, and the law of recrystallization effect by deformation and temperature is obtained. It can be found that number 1 steel had the finest austenite grain size, no matter at which deformation and temperature, which means niobium can obviously handle the recrystallization of deformed austenite. Grain size of austenite at different deformation and temperature is measured to analyze the effect of niobium and vanadium on recrystallization. We can see that with the increase of deformation, the austenite size is refined. The austenite size of number 1 and number 2 are finer, and the difference is not obvious. With the increase of deformation temperature, the austenite size of number 1, number 2, and number 3 steel firstly decreases and then increases. And the austenite grain size keeps finest state at 1000 centigrade. But grain size of number 1 steel, which contains more niobium, remains the minimum size. Morphology of precipitation is observed in this picture. We can see that there are 2 kinds of precipitates in number 1 steel. The large size of niobium carbide and titanium carbide composite is about 100 nanometer. And the small size of niobium carbide is about 10 nanometer. There are also 2 kinds of precipitates in number 2 steel. The large size precipitates of niobium carbide and titanium carbide composite are about 100 nanometer. And there are a lot of dispersed fine small size precipitates of niobium carbide and vanadium carbide composite, which is about 10 nanometer. The size distribution of precipitated particles are calculated. The result is that there are more small size precipitation particles below 10 micron in number 2 steel. The effect of cooling rate and the microalloying elements on the microstructure evolution were studied. It can be seen that cooling rate have an important influence on the microstructure type. Take number 1 steel, for example. When the cooling rate is 0.1 degrees centigrade per second, main microstructure are polygonal ferrite and perlite. When the cooling rate is 2 degrees centigrade per second, main microstructure are polygonal ferrite and granular bainite. When the cooling rate comes to 10 degrees centigrade per second, main microstructure are granular bainite and acicular ferrite. When the cooling rate is 50 degrees centigrade per second, main microstructure are bainitic ferrite and granular bainite. Grain size is finer along with the increase of cooling rate. Phase transformation law is obtained by means of a continuous cooling transition curve of supercooled austenite. With the increase of vanadium content, the polygonal ferrite and granular bainite transformation line moved to the left. the polygonal ferrite face area increased obviously, and the transformation starting temperature increased. Niobium can promote finite transformation, and vanadium can increase the starting temperature of finite transformation. When the cooling rate is 20 degrees centigrade per second, the microstructure of number 1 and number 2 steels are acicular ferrite and granular bainite. At the same time, we have done some wild thermal simulation experiment to study the change of hardness of wild hot effect zone with different hot input. We can see in the picture with the increase of hot input, the softening pitch tends to enlarge, but the increase of vanadium content can weaken this trend. At the same hot input level, the micro hardness of the fine-grained zone increases and the softening pitch decreases with the increase of vanadium content. We speculate that the reason for this phenomenon is related to vanadium precipitate during wild thermal cycle, or vanadium hinders the disappearance of dislocation substructure, but it still needs further experimental verification. To this step, lab research is completed, and based on the result, we have designed industrial production scheme of X80 pipeline steel containing vanadium. Main change is on metallurgical composition. Niobium is reduced to 0.05% from 0.08%, and vanadium is increased to 0.03%. Rolling parameters don't change a lot. Here are some communication with other institutes, such as Shogun Steel and Pangang Steel and Vanadium. The metallurgical composition and the rolling parameters of X80 pipeline steel containing vanadium have been designed. These two steel mills plan to do some industrial pellet production. Communication with pipe channel is that as mechanical properties of base metal and weld of X80 pipeline steel containing vanadium fine as expected. Pipe channel plan to use it in the 4th West to East National Gas Transmission Project. In the end, the summary is that compared with conventional pipeline steel, X80 pipeline steel containing vanadium has the same mechanical properties and better mechanical properties of gas weld hot effect zone. For steel with 0.05% niobium and 0.03% vanadium, the phase proportion of precipitated particles with size lower than 50 micrometer is higher than that of steel with 0.08% niobium. Along with the decrease of niobium content and the increase of vanadium content, it seems that properties of weld hot effect zone such as strength and toughness have been improved. The industrial production guidance program is that main change of metallurgical composition is 0.05% niobium plus 0.03% vanadium instead of 0.08% niobium. As well, ruling parameters are not changed great. And the last, this is the research plan of next step. The main job is to carry out industrial trial production and complete the analysis of microstructure and mechanical properties. Okay, thank you, that's all.
Thank you very much. First of all, I'd like to say that you've done a lot of work there and it's looking very promising. So congratulations on that. We've probably got time for a couple of quick questions. Does anyone have any questions for this presentation? Just a quick question from me then. You showed us some results from welds, and you showed us some hardness profiles from some welds. The objective of this project was to improve the weld HAZ toughness by using vanadium instead of niobium. Have you actually carried out any weld HAZ toughness tests on these steels yet?
Yes, we have do some experimental. We have do some job. The job shows that the toughness of the weld hat effect zone is also improved, but we want to do more job to improve it.
Okay, so we are seeing some improvement in the weld H-affected zone toughness as well as hardness. Is that correct? Okay. Are there any more questions for this presentation?
Hello, it's Birhan here from Sverium. So very interesting presentation. Good properties, but I just wonder also maybe for future it could be nice to present also the let's say the use of these steels in the service environment to check the corrosion properties and possibly also hydrogen transportation.
Yeah, I would hope that the next phase of the project is moving to industrial trials for coil and plate production. So we should hopefully be getting some real information from real pipelines in the future. Is that correct?
Yes, okay.
Okay, well, thank you very much for that. In the interest of time, I think we're going to have to leave this one now. I always say that we can carry on these discussions offline. So if there are any questions, you can email them to me and I can sort of start a sort of virtual discussion going. So please, any questions, just email them to me and I can forward them to the presenters. Okay, well, thanks for that. If you could stop sharing your screen, thank you.